Welcome. In this fourth lecture, we will continue with the fault analysis, review on the fault analysis. We will go with the sequence component also there. We will emphasize here more on this how to calculate the fault current, voltages at different points, and so that we call circuit analysis by drawing the different sequence diagrams and the connections of therein. And then also you can say that we will analyze, you can say that how this such a you can say that platform or tools gives us, you can say that in framing the different numerical leading algorithms and so. Let us you can say that consider a system like this as we have seen earlier also, two sources connected by a transmission line through transformers. So, these are you can say that system available to us. Now, as we have already seen, we will draw the first the different sequence diagram for the system, which will be useful for the fault analysis. So, here you see here already we have discussed about the positive sequence components, positive sequence component of each element of the system. For the generator, you can say that we have a source and the corresponding associated impedance. So, this is source 1. So, Z 1 S 1, Z 1 for the positive sequence impedance of the generator and S for the first source, and then for the transformer the positive sequence impedance Z 1 T 1, and this you can say that for the transmission line impedance Z 1 L, and this for the transformer you can say that second transformer Z 1 for the transformer 2, and Z 1 for the second source G 2 and the associated voltage for this. So, as already we have mentioned that the positive sequence diagram contains you can say that the corresponding sources E 1 and E 2 in this case for this G 1 and G 2. But when you go to the negative sequence diagram, we see there is no you can say that voltage because of the you can say that system the sources being considered balanced in nature. So, there is no negative sequence component. So, each you can say that of the component and they are associated you can say that the impedances negative sequence impedances are provided here. So, Z 2 S 1, Z 2 T 1 for the transformer 1, Z 2 L and Z 2 T 2 and Z 2 S 2. Now, I will go to the negative zero sequence component similarly. Only difference is that you can say that for the transformer the generators, and so you can say that the zero sequence component connection becomes different, and particularly here you can say that two transformers are there and they are associated you can say that the impedances are Z 0 T 1 here and Z 0 T 2 here. Note that here the left hand side you can say that they are star grounded. So, the transformer you can say that impedance zero sequence impedance is connected in series to the line side and the source side, it will be connected, and for the right side you can say that transformer the T 2 one side you can say delta connected. So, therefore, you can say that circulating current will be there. So, that you can say that connected to the reference in this perspective, and this is you can say not connected to the source side because of the in line side of the consider delta connections the zero sequence current will not flow. So, therefore, the corresponding zero sequence diagram becomes like this with associated zero sequence impedances. So, we got you can say that the positive sequence network, negative sequence network and zero sequence network for this for the given system. Now, for different faults as we have already discussed in earlier lecture that for different kinds of fault how the corresponding sequence diagrams will be there and how the corresponding connectivity will be there, that we like to analyze. Now, let us consider for the same system a fault happens to be there in this line from the x portion of the line from the left side and 1 minus x portion from the right hand side with a fault resistance of R f. So, we will consider first the 3 phase balance fault. So, this is a balance fault case. So, therefore, we say that only positive sequence component will be there, no negative sequence and zero sequence as we have already mentioned in the last lecture. So, we have only the positive sequence diagram and the corresponding you can say that fault path has a fault resistance of R f, and in this fault path you can say that an I A 1 fault current flows and we do not have any negative sequence or zero sequence current in this case. So, now you can say that if you like to analyze the corresponding system here, if you see here this is the voltage source with its corresponding polysequence impedance, transform impedance, line impedance up to the fall point from the left hand side x into Z1L, from the right hand side bus 3 1 minus x Z1L, second transformer Z1 T2 and the second source Z1 S2 with its voltage E2. So, for this you can say that diagram, it seems you can say that for this case the corresponding diagram becomes this. So, we can analyze much easier. You can say that instead of you can say that we will going for the 3 phase voltages V A, V B, V C or associated currents and all these things, this diagram. So, once we have this corresponding sequence current in this path, you can find the sequence current from this side also and this side also, different voltages in the systems. Given that in the case of fault analysis, it is considered that you consider the corresponding E 1 with an angle I am saying that magnitude of 1 with an angle of 0 degree per unit, and so also consider these other sources also in the systems with an angle of you can say that 0 degree and magnitude of 1 per unit for the systems. So, with that consideration you can say that the corresponding analysis is being carried out and you can find the different currents and different voltages in the systems. We can go to the consider that other types of fault. Now, in the second one we are going to the line to ground fault case or phase to ground fault case as you say, and let us consider a phase A to ground fault in this case. So, for this you consider the corresponding sequence diagram as you have phase A to ground fault case. Let us for the same system the fault happens to be at F and phase A to ground fault happens to be there x portion from this side and 1 minus x portion from right hand side as we have already discussed in the earlier slide. And with this you can say that for the same system you can say that we have positive sequence diagram, we have negative sequence diagram and we have zero sequence diagram. In the last lecture you can say that we have seen that for a line to ground fault case, phase A fault means you can say that positive sequence phase A for the positive sequence diagram, negative sequence diagram and zero sequence diagram, and we will connect them in series. So, that I 1 equals to I 2 equals to I naught relation is valid, and with that perspective you can say that the corresponding sequence diagram becomes this. So, this you can say that RF should be 3 RF here, and so this you can say that with this you can say that this diagram you can say that we can analyze this circuit, you can say that you can find out I 1 and I 2 and I naught F, and then you can say that you can find the different voltages and currents you can say that in the sequence diagram perspective. Once we have the sequence voltages and currents at different points, we can get back the corresponding phase quantities by the proper relation as you have seen in the multiplying the T inverse you can say that to the matrix. Next, other type of fault BC type fault. So, here you can say that phase to phase fault happens to be there in the B and C phases, and you can say that with a fault resistance of RF, say you can say that. So, we know you can say that for this case that only positive and negative sequence component happens to be there, and therefore, positive and negative sequence they are connected in parallel, and in this case I 1 F you can say that become and that equals to you can say that equals to minus of I 2 F. So, that results in you can say that the sequence diagram like this. Then next one you can say that of the BCG type or phase to phase you can say that to ground, double phase to ground otherwise called also with an RF you can say the resistance here. So, for the system you can say that the same F point it happens to be there, then we have positive, negative and zero sequence component and they are in parallel, and in this case I 1 F equals to summation of I 2 F plus I 2 F, and you can say that I naught F in this case, and you can say that with the corresponding RF and all these things. So, then you can say that we can analyze you can say that each individual you can say that the connectivity here, and you can find the different currents and voltages at different nodes, and we can find the corresponding phase quantities as mentioned earlier case also. Now, let us consider one example here. So, this is a system where we have two sources here connected by you can say that a double circuit transmission line, circuit 1 and circuit 2, and then you can say that they are connected by a transformer you can say that T 1 and T 2, and the T 1 here is connected you can say that delta to the generator side and star ground you can say that to the line side, and the right hand side T 2 is connected you can say that star grounded star current both to the both the sides you can say that in this case, and the corresponding per unit you can say that reactances you can say that of the individual element G 1, G 2, T 1, T 2 and the transmission line T 1 and T 2 circuits are given here, and you can say that we see here you can say that with their MVA rating and you can say that the KV rating of the system in terms of that. So, also you can say that the corresponding reactance through which the second generator is grounded, you can say that also in terms of per unit you can say that 0.03 you can say that is available to us. Now, the task here is that draw the positive sequence, negative sequence and zero sequence networks for the system. For this system, a single line to ground fault in phase A occurs at bus 2 of the network with negligible fault resistance, that is R f equals to 0. Calculate fault current means fault current to the through the fault, line to neutral voltages at fault point. At the fault point, the corresponding line to voltages phase A, phase B, phase C, currents and voltages at generator terminals. Current and voltages at generator terminals. So, the corresponding current and voltages, current supplied by the G 1, current supplied by the G 2 and the corresponding voltages at terminal 1 and 2, terminal 1 and 4 V A, B B, B C at bus 1 and bus 4 are to be calculated. So, now we will see consider first how the corresponding sequence you consider networks you consider being done. Now, you see here consider the fault is being here in this case. Now, the corresponding for this system we have positive sequence, negative sequence and zero sequence diagram. So, you see here consider positive sequence diagram. For this case we have line 1 and line 2 you can say that are in parallel. So, you can say that you see here 2 to 3, 2 to 3 you can say that both the lines are in parallel. So, therefore, you can say that we can make them you can say that one impedance or one reactance as shown here. So, this you can say that with the replacement of you can say that each you can say that impedance or the corresponding reactance you can say that for each element of the systems we get the positive sequence. Similarly, for the negative sequence diagram and you can say that then the zero sequence diagram. In this case this side you can say delta connected. So, therefore, this becomes you can say that open from this perspective and all things. So, that is you can say that with the connectivity diagram. This is a fault of edge type fault. So, therefore, you can say that the corresponding sequence diagram connections you can say that will be in series and then you can say that the R f here equals to 0. So, 3 R f will be here. So, you can say that will be 0 in this case. So, that you can say that the corresponding connectivity. Now, let us you can say that we will try to simplify that diagram to calculate the different currents and voltages in the systems. So, this is about the positive sequence equivalent diagram as you have seen in the earlier one. We assign the corresponding voltages to be 1 with an angle degree, 1 in 0 degree as mentioned. And then you can say that for this case the Thevenin equivalent from the point F if you look you can say that to the left and to the right and then you get you can say that the corresponding Thevenin's equivalent voltage and you can say that the corresponding impedance to be like this. So, this becomes 1 and 1. So, no pre-fault current will be there, no current circulating current in this case will be there. So, therefore, you can say that with again the voltage becomes 1 with an degree and then you can say that the from the left hand side and the right hand side will be parallel 0.06 plus 0.25 in parallel with 0.05 plus 0.07 plus 0.2 you can say in parallel, that gives us you can say that an impedance of 0.157. Next you can say that to the negative sequence component it will be like this. So, from F you can say that again we will see you can say that the corresponding equivalent. So, if you see the equivalent these two circuits will be in this side and this side will be in parallel. So, this parallel you can say that impedance again gives you can say that 0.157 because the positive sequence impedances and negative sequence impedances are same for the both the cases. Now, going to the zero sequence component again from the fault point if you see. So, 0.06 in parallel with 0.15 plus 0.05 plus 0.05 you can say that and the 0.09. So, that gives us you can say that an impedance of reactance of 0.051 for this one. So, we got the equivalent circuit for the positive sequence, negative sequence and zero sequence. Now, I will go for the connections as per we have made for this. So, at F point you can say that they will be connected to an R f equals to 0 you can say that and there we can say that the connection diagram becomes this. So, what you see here that for this case the current which is flowing to the fault point I A 1 F rather you can say that in this case and the I A 2, I A 1 and I A 0 both are all three are same. So, therefore, what you say that from this you can say the diagram we can easily now calculate the corresponding I A 1, I A 2 and I A 0 and also the corresponding V A 1, V A 2 and V A 0. We know here you consider the corresponding V A 1 equals to nothing but 1 with an angle of 0 degree minus this drop you can say that and V A 2 is nothing but you can say that minus of I A 2 into this impedance and V A 0 equals to minus of I A 0 you can say that this impedance. So, that leads to you can say that our from this you can say that sequence you can say that diagram connectivity we can find out this I A 0 to this. 1 with an angle of 0 degree, this impedance plus this impedance plus this impedance. So, that gives us, you can say that the corresponding per unit, you can say that current to be minus of j 2.74. Now, the fault current which is flowing, the current which is flowing to the fault can be calculated in terms of phase A for the phase A, phase B, phase C perspective. From this you can say that sequence component. So, you substitute the sequence component, multiply the T matrix, you can say that, then you will get the corresponding I A, I B, I C like this. Now, what you see here that the I B and I C are 0 and I A you can say that equals to minus j 8.22 per unit. So, this clearly you can say that is in agreement with our, you can say that point that this fault which is we created, you can say that in that system is phase A to ground fault. So, only phase A current is there in the faulted path, phase B and phase C currents are 0. So, with a base current nothing but you can say that base MVA divided by you can say that root 3 VL root 3 VL. So, this relates to you can say that base currents to be 56.07 ampere, and therefore, the fault current becomes equals to you can say that in terms of this magnitude becomes 8.22 into the base current, that becomes 5392.9 ampere current. Now, the sequence voltages at the fault point, because this is you can say that fault is created in phase J. So, we expect the corresponding voltage phase A voltage to be 0. Now, we got the corresponding V A1 and V A2 and V A naught as I mentioned, and then you can say that. So, therefore, you got you can say that different per unit voltages you can say that correspondingly. Now, applying the you can say that the transformation process T into the corresponding sequence voltages. So, we got you can say that V A, V B, V C to be considered in terms of this perspective. So, this you can say that we got V A to be 0 as mentioned, and V B to be considered with 0.891 with an angle of 256.37 degree, and V C to be considered 0.891 with an angle of 103.63 degree. Now, this gives us V A, V B, V C at the fault point. Now, therefore, you can say that we see that we see V A to be 0, V B consider that phase voltage you can say that will be in terms of 220 by root 3, we go to the voltage quantity in terms of the kV. So, in terms of the per unit base voltage into per unit, that gives you can say 113.18 with the corresponding angle, and B C you can say that again 113.63 you can say that with an angle of 103.63 kV. So, at fault point you can say that in terms of this kV you can say that we got the corresponding voltage to be this. So, these are you can say that obtained you can say that from the sequence component voltages as obtained from the considered sequence diagram perspective. Now, the next you can say that we will see how the corresponding generators contribute you can say that to the fault current contributions and the associated voltages at the bus terminal and so. So, but for the consider generator 2 you can say that the contribution. So, here you can say that the components of I1 flowing toward bus 2 you can say that from this one you can say that how much current is flowing through is nothing but you can say that this current, because this current from this part, this current, this fault current we have already found out. So, current contribution from this side and this side. So, that is nothing but you can say that because both are having one per unit you can say that with an angle of 0 degree. So, it depends upon the parallel path combinations, and therefore, you can say that this I1 current into impedance of this side divided by this impedance of this plus this, and that gives you can say that the corresponding current to be minus j 1.35 contributed from the G2 side. The components of I2 flowing towards bus 2 also you can say that it will be same, because IA2 equals to IA1 and the impedances are you can say that in both positive and negative sequence components are same in for this problem. So, therefore, you can say that we say that becomes also minus j 1.35 per unit. The components of I naught you can say that which is flowing from this side is nothing but for this one I naught equals to I2. So, therefore, minus j 2.74, again this is a parallel combination. So, therefore, this you can say j 0.6 divided by the sum of this impedance, sum of the reactances, and this. So, this gives you can say rise to I naught from the generator 2 side you can say that becomes equals to j 0.39 you can say that per unit. Now, so therefore, the line current terminals from the generator 2 finding from the sequence component perspective, multiply the T matrix you can say that we can get the IA, the IC contributed from the generator 2 side you can say that becomes 3.09 in phase A, 0.96 in phase B, and 0.96 you can say that with an angle of 90 degree in phase C per unit. Base current for the generators 250 MVA, and the voltage you can say that base voltage is 11 kV. So, therefore, you can say that if you get the corresponding base you can say that current 13,121.59 ampere. So, multiply this base you can say that currents to these per unit values, you get the corresponding set of currents for the phase A, phase B and phase C contributed from the generator 2 sides. Similarly, at generator 2 also we can find out the voltages V A naught, V A 1 and V A 2. At this you can say that terminal, you can say that at the terminal you can say that noted here 4, node 4, and then you can say that from these calculations this minus this voltage minus this one, and therefore, you can say that this you can say that V A naught, V A 1 and V A 2 you can say that we got to consider like this, and then after the sequence components are obtained you can say that multiply the T matrix, we get the phase A, phase B, phase C, you can say that phase voltages at different phases you can say that, and they are found out to be 0.405 with an angle of 0 degree, 0.91 to 51.8 degree and 0.91 you can say that 108.2 degree per minute. So, we know you can say that the corresponding base voltage for this you can say that this case 11 by root 3 kV, and we multiply the corresponding sequence component to each one, and then you get the corresponding voltages associated with phase A 2.57 kV, phase B you can say that 5.78 and phase C also 5.78 kV at you can say that node 4 you can say that which is connected to the generator terminal 2. Similarly, for the generator you can say that G1 side you can say that the corresponding currents can be obtained. The current contributions you can say that from the generator 1 in positive sequence, negative sequence and zero sequence, the parallel path combinations as you did for the generator 1 perspective, and that is why I 1 becomes equals to minus j 1.39, and you can say that similarly you can say that you can find out the I 2 also, and also you can find out the I naught also. The delta star transform you can say that there will be phase shift of 30 degree you can say that for this case. See here you can say that because the transform you can say that which is there in the G1 side is having a delta star delta into the generator side and star to this one. As far as you can say that from the analysis and convention you can say that if you are going from you can say that low voltage to the high voltage. So, in the positive sequence you can say that voltage and currents we have plus 30 degree, and if you are going from you can say that from the high voltage to the low voltage it is minus 30 degree, and in case of negative sequence you can say that diagram it is the reverse you can say that in reverse to that of the positive sequence perspective. So, therefore, you can say that in this case the phase shift of minus 30 degree is taken into account. So, therefore, you can say that whatever voltage we are getting 1.37 with an angle of you can say that 270 degree minus of j. So, 270 degree minus 30 degree that gives us 1.39 with an angle of 240 degree. The phase shift or IA 2 as mentioned you can say that because you are going from the high voltage to the low voltage. So, therefore, IA 2 you can say that plus 30 degree. So, IA 2 you can say that 1.39 to 70 degree, same as you can say that I 1 as I mentioned plus 30 degree that gives you can say that 1.39 300 degree, and thereby you can say that we got the you can say that the corresponding sequence component, zero sequence, positive sequence and positive sequence and negative sequence. Zero sequence component is not available because the delta side connections. So, therefore, you can say that substituting these values and multiplying the T matrix you can say that we got these phase components I A, I B, I C at generator terminal G1, and that gives us you can say that a value of you can say that 2.41, 2.40, 2.40, 270 degree and 0 you can say that to the per unit value perspective. Now, we see here the fault was you can say that in phase A only in the transmission line, but you see because of the delta connections the get you can say that there are two you can say that currents you can say that in both you can say that currents in phase A and phase B. Now, multiplying the base currents for this generator 1 you can say that we get the corresponding value of you can say that phase A current in terms of amperes 31491.81 ampere in both phase A and B, IC current being 0. For the voltage calculation also similar to you can say that what you did for the generator 2 also we will do you can say that for the positive sequence you can say that perspective 1 minus this drop you can say that will give right to you can say that minus 0.65225 you can say that this V A naught you can say not available you can say that because of the short circuit perspective, and then you can say that we have you can say that the V A 2 you can say that we will calculate the corresponding drop here minus of this gives that to this. Now, in addition to that as already mentioned we are going from the high voltage to the low voltage. So, therefore, you can say that in the positive sequence diagram we put you can say that the minus 30 degree perspective, and for the negative sequence you can say that value we get the corresponding plus 30 degree perspective, and considering those you can say that angles and all these things we get the corresponding V A 1 and V A 2 in per units like this. and then you can say that to the phase component VA, VC, multiplying the T matrix to the sequence component, we get the corresponding power unit, you can say that voltages for this case. And then you can say that finally, multiplying the, you can say that the base voltage of 11 by root 3 kV, you can say that we got the A, B, C components for this system, and that you can say that therefore, you can say that we got 3.59 kV for the VA, 3.59 kV for the B, and 6.35 kV for the phase C voltages. Now, this from this above analysis, you can say that we say that for a given fault in a system, we can get the corresponding fault currents, fault voltages in different phases, and also you can say that at different nodes you can get the different currents and voltages, including that for the generator terminals and so. So, that gives a platform, we can say that for fault analysis, and thereby I can say that which will be beneficial to the relay and any protection system perspective and all these things. So, we see you can say that at any you can say that protection, you can say that arrangement at any node, or you can say that for any transmission line, or you can say that any element like generator, or you can say that transformer, the circuit breakers that has to be fixed, you can say that depends upon this associated current at that point and the corresponding voltages and so. So, that you can say that therefore, that is this fault analysis is being very much useful for circuit breaker rating specification and so, and other details of the circuit breaker. Relay settings, how much you can say that minimum current, maximum current, we will see you can say that in details further classes, you can say that about that that becomes very useful you can say that tools for you can say that for relay settings perspective. In addition to that, you can say that this analysis is very useful for numerical relays. How that is, you can say that we will see right now. Let us you can say that analyze you can say that the system for a case you can say that see here, this you can say that phase A, phase B and phase C values are given to us. So, obtain the sequence component for the 3 phase fault. This is a 3 phase fault IA, IB, IC. So, magnitudes are same and they are 120 degree apart. Now, what we say conclude that if we calculate the sequence component using the T inverse matrix for this one, as you have already done. So, for this case you can say that the corresponding zero sequence component is 0, positive sequence component is same as you can see that the corresponding IA as you have already seen earlier also, and the negative sequence component is 0. So, only you can say that we see here which component remains for the balance fault case, only positive sequence component remains, and that becomes same as you can say that phase A you can say that current you can say that for this case. Now, for you can say that case like this we see here you can say that line to ground fault phase A only is involved with the fault, IA is only there, IB and IC are 0, and by analyzing you can say that this what you get you can say that is that IA naught, IB naught, IC naught all are having the you can say that same magnitude and angle. So, we see you can say that the relation for this is I 1 equals to I 2 equals to I naught, and they are become I by 3. So, that you can say that is the case. The other case you can say that you see here IB you can say that equals to this, and you can say that IC equals to this, and if you analyze you can say that we see here no more you can say that I current. So, fault is involved with only B and C. So, you see here you can say that in this case IA you can say that I 1 equals to minus of IA 2. So, this you can say that is nothing but for the BC type of fault you can say that. So, for the BC type fault we see that the corresponding sequence component has a relation like this, and for the BCG fault to be like that you can say that for this case B and C phases are involved with fault, A is not it, and it is involved with the ground also. So, by analyzing this you can say that I 1, I 2 and I naught we get you can say that I naught is also available here because ground is involved, and finally, we conclude that I 1 equals to minus I 2 plus I naught. What you can say that conclude from these relations you can say that the positive sequence you can say that quantities you can say that are present, only positive sequence quantities are present for the balance loading condition or balance fault condition, 3 phase bell fault conditions. Negative sequence quantities are you can say that measure of amount of unbalance, or it say that is available during any unbalanced fault. For any unbalanced fault negative sequence is available. Zero sequence quantity is available whenever a ground is involved with the fault, and you can say that both zero sequence and negative sequence are available for you can say that for any unbalanced fault involved with ground. So, this you can say that relations you can say that what we see here is very much useful for to identify the different types of fault which is being used in different relay applications and so. So, therefore, the sequence component also reveal you can say that information on the fault behavior given at a given instant of time. These fault analysis on the relay applications, how that is useful, let us you can say that try to have a look on this. Now, negative sequence you can say that overcurrent relay is being useful you can say that for system unbalanced conditions, because any system unbalanced conditions means you can say that from the generator side, or you can say that any you can say rotating device, negative sequence current means you can say that the corresponding rotor gets heated, and therefore, in a long run time long run perspective this becomes detrimental. So, really you can say that in that case can use you can say that negative sequence component, and then you can say that it can trip the circuits for protections. For transformer protection, the faults involving with ground, the transformer the fault involving ground means zero sequence component will be available, and for many you can say that winding protection of the transformer you can say that zero sequence component is being used in terms of that. Now, let us you can say that to how directional for directional link purpose you can say that negative sequence component is being very useful you can say that. See this you can say that sequence diagram which we have used earlier also you can say that let us you can say that see you can say that you can say that a line to ground fault case, and then you can say that a fault happens to be there any of the point, and then positive, negative and zero sequence diagram is connected you can say that with the 3 times of the fault resistance you can say that perspective, and we have connected like this. So, see here you can say that when you talk about negative sequence diagram, let us say the relay position at bus 2 and a fault has occurred to the right hand side of the relay at this point. So, then you can say that we see that the corresponding current I2R is flowing from bus 1 side to the bus 2. So, the corresponding you can say that the corresponding relations for this you can say that is that the Z2R which will be seen by the relay, the impedance which will be seen by the relay will be V2R divided by I2R, but this V2R you can say is being expressed in terms of you can say that minus of you can say that I2R into the Z2S1 plus Z2T1. So, therefore, you can say that this at this point you can say that the Z2R you can say that which will be observed by the relay at this point becomes negative. Now, in another case you can say that when the fault happens to be the left of the you can say that relay position this one, then you can say that the corresponding fault current you can say that will now you can say that will be flows from this side to that side you can say that through the relay point. Considering the you can say that the positive direction of current you can say that for the relay to be I2R in this case. So, therefore, you can say that the impedance which will be observed by you can say that noticed by the corresponding relay at that point you can say that the Z2R becomes positive. So, negative sequence impedance based relay you can say that which is being widely used you can say that in network protection distinguishes you can say that fault in the forward direction and reverse directions by calculating the corresponding sequence impedance and negative sequence impedance Z2 from the you can say that associated voltage and currents. So, this gives us an idea about that there are numerous scopes you can say that for the usage of you can say that sequence components in the numerical link perspective. A list of you can say that device number as we have already mentioned earlier also, that these are overcurrent relays you can say that instantaneous, and you can say that time overcurrent relay 50 and 51 you can say that involved with ground. So, zero sequence current is being used, and 52 you can say that this 2 refers for the negative sequence component. So, negative sequence current is being used you can say that for the overcurrent relay principle. 60_2 this 2 refers to negative sequence you can say that directional you can say that overcurrent relay, either you can use zero sequence component or negative sequence as we have already discussed in the earlier slide. 21 for the distance link perspective, ground distance relay you can say that uses you can say that different frequency different sequence components for a successful decision making process. 87 for the different I am say that the differential protections uses different sequence component for restraining purpose, and negative sequence component also is for you can say that the decision process and all these things. 46 is phase unbalance, and like that you can say that negative sequence over voltage, and so there are so many you can say that relays you can say that provided by the manufacturers you can say that today using the sequence component for this perspective. So, this is all from the lesson 4 you can say that for the how the sequence component you can say that is being useful in fault analysis, and thereafter how they can be used for the applications to different numerical drilling principle. In next class, we will have a general background how a numerical drilling platform is being prepared. Thank you.